Hi there, my name is Charles Sipa. Welcome to another presentation of our e-tutorial series. Our focus today is on growth and decay. But before we can understand growth and decay, I think it's important to recap some important ideas about functions. Let's say we've got a system of axes, like here in this case, our horizontal axis is marked t to indicate the time variable t, and our vertical axis y is marked f of t, which gives us the amplitude of the function f of t at a particular time. So I would like to sketch a graph of function f of t here, which you can simply say y is equals to f of t. And on the other hand, I would like to revise, or some people might be meeting for the first time, this we say a function is growing or is increasing if, let's say, we've got t1 here and t2 there. Remember, from the left to the right, numbers are increasing. So we'll say a function is increasing if clearly here we see that t1 is less or equals to t2. Then if this implies that f of t1 is less or equals to f of t2, then we say the function f is increasing. Otherwise, if this condition is still the same, and we get that f of t1 is greater or equals to f of t2, then we would say the function is decreasing. So if the function is decreasing, the other way of saying that, you can say the function is growing. So now let's look at the following graphs. So let's say we've got we could have a curve here this way, or even a line maybe drawn this way. What we can say here is that whether the function is linear, like giving us a straight line like this, is increasing, and then this one also is increasing. So now these two functions here, these two graphs here, indicate what we would say is growth. So we experience growth in this situation here. But in this case, we have particular growth which we can call linear growth, and another growth which at this moment you can just leave it at that. And on the other hand, you can have a graph like this, then you've got a curve coming this way, a curve of function, or if it's not it's just a curve, we could also be having a line, let's say a line which runs like this. So again here, what we experience in this case here, we could say we experience a function which is increasing, or we can talk of decay. In other words, so those are the two situations, or there's two opposing situations. And on the other hand, we can also have a function in this form, which is a line, which is horizontal. In this case, that's the function which you say is a function which is a constant. Now it's cutting at a certain level here, and it maintains that. Then that will be a function which is a constant. Now here there's no growth. We would say now here growth is 0, but there's decay, and there's growth. So here there's no growth, there's no decay. So I hope it's important to differentiate the three cases. When we've got growth, which means the function is increasing, or here the function is increasing, and when there's decay, we're talking about a function which is decreasing. Now in the situation where there's no growth, no decay, then we say the function is constant. Okay. Now to sort of experience a certain type or special type of growth, let's look at the following situation which we meet in biology. Now we all know that a cell is a basic unit of life. Now is the smallest living thing, which is a cell, which involves multiplication of cells in our bodies can result in increasing of tissues, and that way we can grow and so on. But then let's just focus on the multiplication of cells themselves. So what do you know, that a cell has got this kind of a schematic structure whereby we've got the nucleus in the center, some kind of liquid here which is sort of supporting the nucleus, which is enclosed in a thin membrane here. So what happens is that, what we're taught in biology, that is for cells to multiply, in other words, to increase in number. What happens, the cell will actually grows to a certain size where it starts assuming a certain shape, which leads to actually breaking into two parts. So the stages here, this is maybe the initial stage, the second stage we see it growing, in the third stage we see it almost looking like two cells, and it goes on until it breaks the nucleus, and the nucleus, when they're broken, they're two like that, the membrane also will sort of cut, then we get into two cells. What this tells us, the situation tells us that one cell, through its one life cycle, which could be a unit of time like a day or another time interval, the cell over one life cycle, the cell will multiply from 1 and divide into 2. So that we can describe it in this way schematically. So let's say here we've got cell population. Now we've got one cell. We're just observing the growth starting from one cell. So this is day 0. Now it's our initial day, and we can say here is the t equal to 0. In our initial time. So over a life cycle, let's say in this case we're going to assume that the life cycle of a cell is a day. So from 0 to day 1, that is, there's a duration of a day there, this cell will divide into 2. And then day 2, each of the cells, assuming obvious this is kind of an experiment, we assume nothing goes wrong, each of the cells will divide into 2. And then in day 3, the 4 cells which are already there, they also divide into 2, and the day 4 and day 5 and so on. Now if you look at the population, now is population per day. Now is, in this case here, we say P at 0. Now is population on the initial day, we can see that is 1. And when on the second day, we see that the population is now 2, and the third day, so this is day 0. Now this will be P at 1 after 1 day, population will be 2. Then after 2 days, then that will be 4, and you can see that it continues there, it goes to 8 and 16, and up to this 5 year, we've got here 32. Now if we monitor this pattern, is growth. We started at 1, it increased to 2, it increased to 4, increased to 8, 16 and so on. But let's notice something here, that all these numbers are powers of 2. Then we've got here 2 to the power 1, and there we've got 2 to the power 2, and there we've got 2 to the power 3, 2 to the power 4, and this will be 2 to the power 5. Now this will continue to population on day n, that will be equals to 2 to the power n. Now if we start now going backwards, we go 5, 4, power 3, power 2, power 1, and here this agrees with the fact that 2 power 0 is equals to 1. So this is kind of a growth, and as you can see, this kind of growth we can express it exponentially. Now this is in exponential form, so such growth we call it exponential growth. But I think what will be interesting is that how do you take it, or what kind of a shape we get when we try to produce a graph more or less like this. So let's move on to this situation here. So I think what we have had there, we can now represent it graphically like this. We saw that on day 0, the population of cell was 1. So we had a point there 1, and then day 1, that cell divided into 2, then the population was 2, and then on day after 2 days, the population was 4, and it continued from 4, increased to 8, and on 4th day, it was 16. So as you can see, we've got some kind of, we've got growth, which is like that, and this is what we normally call exponential growth. So I hope you can see now that here we can take this as function Pn, since we're talking about population, is equals to 2 to the power n. And we can see that this is growth. Now, what you can see here, which is very important, is that our 2, which is our base here, is actually greater than 1. So we know that this kind of operation of exponentiation of numbers is something which we know. So we can also consider that what would happen if we take this base maybe as a number a between 1 and between 0 and 1. Now let's take, for example, half. Let's say this base was half. We would write that as 1 over 2 to the power n. But we also remember that 1 over 2 can be written as 2 to the power 1. And then if we elevate that to the power n, this would come as 2 to the power minus n. Now, if we check this now, what will happen at 0? I think this would still agree that this is 0. Now at 1, at 0, sorry, at n equal to 0, we will agree that this number would give us 1. But at 1, we would have half to the power 1, and that will be half. And at 2, we'll have half to the power 2, which will give us 1 quarter. And I hope you see that the next value will be 1/8. So which means the values now will be decreasing. So what we have there, we have got some kind of we've got actually what we can describe as decay. In this case in particular, is not just any other decay, but an exponential decay, because this decay is described by an exponential function, where in this case we consider the base between 0 and 1. So that we can graphically illustrate as follows. I hope you noticed that the previous case of cell population multiplication we saw was giving us a kind of a discrete function as isolated values. But if you consider exponential function in general, I hope you remember that if you've got an exponential function y, let's say in this case y of t is equals to a to the power t, where t is where a is greater than 0, what would happen? We would get a function which grows from minus infinity, and the shape will be like that, of course having an intercept there at 1. And on the other hand, if it's a decay, the shape of the function will be from minus infinity be decreasing and going that way. And then we've got here what we call exponential. I will just write exponential decay, and there would have an exponential growth. So the terms growth and the decay, they're just equivalent to saying the function is increasing or the function is decaying. So I think with the cell population, you've seen an example of what is exponential growth. But also, if you do some experiment, if you take let's say a cube, an ice cube from a refrigerator of a certain mass or volume, you will see that if you monitor the volume with time, the volume will decrease exponentially, and that will be what we call exponential decay. And exponential growth and exponential decay are very important kind of functions which are used in science and in engineering for modeling a lot of phenomena, especially like one good example, even the population of human beings itself can be described by an exponential function. So now let's continue this way. Now let's come to recall the issues on derivatives of functions. So talking about derivative of a function, I think you remember that when we did calculate derivative of function, we considered this incremental constant. Just say we had t there, and then somewhere here with t plus an increase in t. Now it's the distance between these 2 points is what we call an increment in t. So to get the derivative of a function, we calculated the limit of this incremental quotient, which was f of t plus increase in t minus f of t divided by the increase in t. I think you remember in some cases we use the h, but it's actually the same thing. We are talking about the change in the independent variable. So what we've got here, this is a ratio which expresses a ratio between the increase in the value of the function over the increase in the independent variable. Now its limit, which we calculated if existed, we said this limit as change in the independent variable is equal to 0, is what we're going to call f prime of t, other the derivative of the function. And the most important, I think in this case, the most important interpretation of this derivative is to interpret the derivative of function as what we call the rate of change. In this case, is the rate of change of the function with respect to its independent variable. So where does that take us to? I emphasize that this interpretation of looking at the derivative as the rate of change of variable is very, very important. Another idea or another concept which is very, very important also is that of proportionality. I hope you see that when we're dealing with functions, like we plot functions on system of coordinates like that, like say x and y, you can see that functions actually join these two variables. They describe how these variables, or let's say the dependent variable y, depending on x, how they change. But sometimes we need to see the relationship between the two variables. So let's say we've got a variable x and a variable y. So this could be two different things, maybe which are related, and maybe y increasing or decreasing in terms of x. To say y is proportional to x, then we write y is proportional to x. Now, that is a statement which you can say, like we're saying it verbally, y is proportional to x. But mathematically, we must understand that when you say y is proportional to x, we mean that there exists a constant, let's say constant k, such that you can express this relationship via this equation. Y is equals to k multiplied by x. So that would be saying that y is proportional to x. So we remember at school we did direct proportionality. Actually, this is direct proportionality. We also have got inverse proportionality, which you can also revise. But in this case, I'm reminding you of this direct proportionality because I want to take you to the first manifestation of differential equations in this course, maybe, which is something new. A differential equation is simply an equation in which derivatives of an unknown function appear. Like, for example, let's say we got a statement like this, which I think we have seen in your text, which says the rate of change of a function y of t. But when we've got a function y of t and we talk of its rate of change, which means then we're talking of y prime of t. Now, is the derivative of y with respect to t, which you can also write as dy dt. So I repeat that the proportionality and derivatives you have written, I think they lead us to the first manifestation of differential equations. Like, for example, a senior statement which says the rate of change, in this case, which we're talking about a derivative of a function y of t, is directly proportional to 1. So now if we say the rate of change of a function y, such as y prime of t, is directly proportional to y of t. So from what we've just seen, this means that there exists a constant, let's say constant k, such that y prime, let's say y prime of t is equals to k multiplied by y of t. So now this expression we've got now, because of the appearance of a derivative here of a function which you actually don't know, we'll call this a differential equation. I would like to repeat this. The expression like this, because of the derivative here of an unknown function yt, we call this a differential equation. And in this case, it's an equation of with a differential equation with respect to t. We can also express this as dy dt equals to k multiplied by y of t. But now I think it's more interesting to look at it is in this form, because equivalent to this expression, y prime of t equals to k y of t. This is equivalent to y prime of t over y of t equals to a constant k. And this expression here, I think is very, very important for us. What you can see here is that we've got 1 over y of t multiplied by y prime of t. I think you should be now recalling that we made this kind of expression when we're dealing with the derivatives of special functions, which are logarithm functions. So once we talk logarithms, in this case, let's say talk natural logarithm. Once we talk logarithms, I think we shouldn't lose sight of that logarithm functions are closely connected to exponential functions. So at this stage, I'm going to stop here, hoping that you understand what we mean by growth and how derivatives and proportionality lead us to the manifestation of differential equations. Otherwise, at this stage, I would like to say thank you for listening.